So the lag compensator electrical network looks like this, comprises of R1 connected to the series combination of R2 and C, and the input is applied to R1 point and the reference point, and the output will be observed across R2 and C together. So if you look into the derivation part to derive the transfer function, and obviously the question is, why do you need the transfer function? Because we are going to study the frequency response. We are trying to achieve the frequency response experimentally. Before that, if you want to know how exactly the frequency response of lag compensator will be, then that is possible by using Bode plot technique. For Bode plot technique, you need transfer function. So if you simplify these two, this is what you are going to get. And then this is nothing but a divider network, treating this as one impedance and this as another impedance. So V naught of S is equal to V in of S into this impedance, that is nothing but this part, right, divided by this plus this, R1 plus so and so. So if you simplify it, then it takes the shape of V in of S into R2CS plus 1 divided by R1 plus R2 by R2 into R2CS plus 1. So treating R2 into C as tau, it is written as tau S plus 1 numerator part, and here you have one term R1 plus R2 by R2. This is treated as beta into again R2 into C is tau. So beta into tau S plus 1. So the transfer function becomes V naught of S by Vn of S is equal to tau S plus 1 divided by beta tau S plus 1, where tau is R2 into C and beta is R1 plus R2 by R2, which is greater than 1. If you recall the explanation of lead compensator, there was one term known as alpha. Alpha is the ratio of R2 by R1 plus R2, which value is less than 1. If you compare alpha and beta, you can observe that beta is nothing but the reciprocal of alpha. Here it is less than 1 and here the beta value should be greater than 1. And if you construct the Bode plot with the help of this transfer function, then your Bode plot looks like this. Initially, for lower range of the frequencies up to the frequency that is lower cutoff frequency 1 over beta tau, you have beta tau, one of the corner frequency in this case is 1 by tau, another corner frequency is 1 by beta tau, right? And up to 1 over beta tau, the magnitude remains same, and from that point onwards with respect to the frequency, it starts decreasing with a slope of minus 20 decibels per decade, and when it reaches 1 by tau, the another cutoff frequency, the higher cutoff frequency, again the magnitude start remaining constant. This is magnitude versus omega, that is frequency. Similarly, if you look into the phase shift, the curve, it varies in this way. Remember, here all angles are negative because it is lag compensator. Output will be lagging behind the input and hence the angle will be treated as minus. Whereas in case of lead compensator, output leads the input and hence in that case all angles are considered as positive. So here the maximum phase shift appear at a frequency called omega m. I am using the notation omega suffix m because this is the frequency at which the phase shift is maximum. The phase phi is the notation for phase shift and phi suffix m stands for maximum phase shift. It occurs at a frequency that is omega m. So it varies in this way. It starts with almost 0 and then it reaches its maximum value in the negative scale, and as you increase the frequency further, again it will start decrease and it becomes equal to 0. So this is how the frequency response of lag compensator looks. Now let's move to the design part. In the design part, we have again 4 equations as in the case of lead compensator. Tau R2C, beta R1 plus R2 by R2. Already you are familiar with these two expressions in the derivation part of the transfer function. The another expression for beta is 1 plus sin phi m divided by 1 minus sin phi m. In fact, in lead compensator, alpha is given by the reciprocal of this 1 minus sin phi m divided by 1 plus sin phi m. Here it is just reciprocal of that 1 plus divided by 1 minus. Omega m is 1 over square root of beta into tau. So these are the four equations that you should use when you are going to design the electrical systems for the lag compensator. Yeah. So the data what we required for the design is the frequency at which the maximum phase angle occurs. So here for an example, I have taken phi m as 45 degree. That means the phase shift between the output and the input should be 45 degree, which should occur at a frequency say 300 hertz. So first you start with in equation number 3. Since you know phi m, using this equation 3, you will get the value of beta. It is 3, it should be greater than 1. You can cross check your answer. At any cost, beta value should not be less than 1. Then you need to go for equation number 4, for which you required omega m, but in the data fm is given. So you can convert that fm into omega m by multiplying it by 2 into pi, it is 1885. So now you go to this equation, substitute the value of beta and omega m, you can calculate the tau. Remember always the tau will be in order of milliseconds, 0.3060 millisecond for this given data. Then using these two, you can move to equation number 1. So you know the value of tau. You need to decide the values of R1, R2 and C which are involved in the circuit. So to find R2, assume the value of C as 1 microfarad. C value, you assume it as 1 microfarad, and hence you can get the value of R2 which is 306.3 ohms. Knowing the value of R2 and beta, using equation number 2, you can find the value of R1, that is 612.587. So immediately after the design, you should draw your circuit diagram with the designed values. So I address this circuit as a practical circuit diagram. What I have drawn here is theoretical circuit diagram, R1, R2, C, and it is shown as Vi and this is shown as V0. But here all values are mentioned and what is the input source that what you are going to use. In fact, it is the signal generator with the desired frequency, right? And output we are going to use the CRO to monitor the output. That is what we should show here. Your input is signal generator with what is the peak to peak value you are. The input is signal generator with the V peak to peak value, whatever you set, say it is 4 volts. And anyway, here the frequency is variable as you are going to take the magnitude and phase shift with respect to the frequency. And output is the CRO. So your tabular column looks like this. You are going to achieve the frequency response. So you should vary the frequencies. The first column is frequency. And when I say frequency response, there are two plots, what I have explained here, magnitude versus frequency, phase shift versus frequency. So you need to find out magnitude and phase shift for various frequencies. So for various values of frequencies, in order to get the magnitude, first you should measure V0. Anyway, V in is kept constant, say at 4 volts. Any value you can take, but 4 volts is comfortable. If you measure V0 for all individual values of frequencies, using that V0 and V in and by taking 20 log, you can find the magnitude for each and every individual frequencies. That is one value that you need to measure from your CRO. Second, delta T. It is a time difference between the starting point of the input and the output. Lag compensator means your curve looks like this. If the input is like this, output is lagging behind, it starts after the input, your output comes like this, right? So there is a time difference between the starting point of your input and the output, that I am naming it as delta T. And this time difference varies with respect to the frequency. So for each and every individual value of frequencies, you measure along with V0 peak to peak, you measure delta T also. In lead compensator experiment, I have explained how to convert this delta T into phase shift. So final equation for that is 360 degree into whatever the frequency you have, that into whatever the delta T you are going to measure. So you will get phase shift. So if you plot this magnitude versus frequency, you will get this part of the plot. Similarly, if you take the phase shift and the frequency versus frequency, you will get the second part of the part. Now let's move to the experimental setup. Okay. I am using one channel of the CRO to observe the input, as it is required to observe both input and output simultaneously on the screen. So this probe is connected to the R1 point to which the input is fed. So these two are shorted and it is connected to it. And the other end should go to the reference point. So these two should be connected, and let me use one small additional wire and right. So input, to observe the input, this probe is connected between the point where the input is fed and the reference point. This is what your reference point. And now you need to use one more probe to observe the uh, output. And where are you observing the output according to the circuit diagram? Between R2 and C, not across C. You are measuring it across R2 and C. So it should go to the junction where R1 and R2 are meeting. So R1 and R2 are meeting here, this point and this point, both are one and the same. So you can connect this probe either to this point or to this point. Okay. So in order to observe the output on CRO, I am connecting the CRO probe to the junction where R1 and R2 are meeting, and the another end obviously should go to the reference point. Right. So circuit connection is over. It is very simple. Start with R1 to which the input is fed. The another end of R1 should go to R2. The another end of R2 should go to capacitor positive terminal. Negative terminal of capacitor should go to the reference point. And input from signal generator is fed to R1 point, and by default the another terminal of your probe should be connected to the reference point. And in order to observe both input and output simultaneously on CRO, I am using two probes, and this is your input channel. So it is connected to the point where input is fed, and the other point by default it is connected to the reference. Similarly, the another channel we are using it to observe the output. So the positive terminal of the probe goes to the junction where R1 and R2 are meeting, that is nothing but this point or this point. So I am connecting it to here, and another terminal of the probe is connected to the reference. So your circuit connections are over. Okay. Before going to start the experiment, first you need to set the values, and according to our design R1 is 612.587, but since simply if you are going to take the help of these markings, you may not get the exact value. So use your multimeter to set the exact value according to your design, but make sure that one terminal of your decade box is free from the connection when you are using the multimeter. Otherwise, you don't get the proper value. So, according to this value should be 612, and if you set it to 6, let me make these to 0. It is what you are getting here 602, but I want 612. Let me increase this one to 10. You are getting exactly 612 now, right? You need not to adjust the third knob, right? Because of the tolerance, in fact it is 610, but you are getting it as 612 what we required here. This is enough. Okay, so one decade box setting is over. If you move to the second decade box, that is R2, that is 306. So this is set to 3, and in fact this is 0 only, and what we need is 306. Let me move to this. So 305.6 you are getting, and if you move to here 306.5 or 4 you are getting. So this is almost closer to the value what we have got it in the design. Okay, so this part is over, and the capacitance box is set to 1 microfarad. Okay. So according to the data, the frequency given is 300 hertz. So the signal generator, we have chosen sine wave as an input with the frequency which is 300 hertz. So first, before going to start your experiment, make sure that you are getting a proper sine wave by feeding your signal generator, directly connecting it to the CRO, and set your V in peak to peak value to a certain value. So I have taken in this case as 4 volts. It is exactly from positive peak to negative peak, it is 4 volts. And since it is 300 hertz, so whether your calibration knob in your CRO is set or not, to make sure that you measure one complete time period here. In fact, 300 hertz reciprocal is 3.33 millisecond. If you measure one complete cycle, 1, 2, 3, it is 3.3 is there. That means it is an indication that your CRO is calibrated. So in this experiment, you are going to take the reading along time axis. If you don't calibrate your CRO, all your readings will go wrong. So make sure that your CRO is calibrated before you are going to start your experiment. So it is now for 300 hertz, here one complete time of your sine wave is 3.33. It is an indication that your CRO is calibrated. So now let's see how to see the output. So one more channel I am using. So that is, according to the circuit diagram, CRO should be connected across R2 and C. In fact, this is the junction where R1 and R2 are meeting, and this is nothing but your reference point. So the positive point of your CRO, it goes to the junction where R1 and R2 are meeting. And the negative point, obviously it goes to the reference point where your capacitor terminal is connected. So let's see how the output is. I am activating the output channel and release the ground button. You are observing the output here. So it is basically a lag compensator. Lag means output, starting point of the output should come after the starting point of the input. It is an indication that output is lagging behind the input. So you need to consider the starting point, which comes first. So here input occurs first and then the output. So output is lagging behind the input. In this context, we call this as a lag compensator. So now we need to measure the phase shift. According to the tabular column, what I have explained, for various values of frequencies, you need to measure V0 peak to peak, that is your V0 peak to peak. That is one data that you need to measure. And once if you measure this, considering the input which is kept constant, take the ratio of V0 and Vin, take the 20 log of that, you will get your gain in terms of decibels. So one of the plot in our frequency is magnitude versus frequency. So measuring V0 peak to peak and converting that into a gain with the help of Vin, which is kept constant, you can plot the magnitude versus frequency. The another plot is the phase shift versus omega, the frequency. For that, you cannot measure the phase shift directly from the CRO. Here what you can measure is only the time period. So the time difference between the starting point of the input and the output, I am addressing that as delta t. So you need to measure delta t, and using this standard equation, what already I have explained in the lead compensator circuit, convert this delta t into phase shift. Then using these readings, phase shift versus frequency, you can construct the second plot of, right? So this is going to complete your frequency response. So now let us see how to measure delta t. So according to the design, when frequency is 300 hertz, you have designed your circuit in such a way that when the frequency is set to 300 hertz, phase shift should be equal to 45 degree. Let us see whether it is equal to 45 degree or not. So it is very small, so we need to measure it accurately. Let me move to the lower multiplication factor from 1 to 0.5, right? What is happening when you move from 1 to 0.5? Of course, this time period, the gap between this is getting expanded, but at the same time these lines are going to get inclined more. Obviously you will get confused whether it is passing through a point 2 or 0.3, something like that. If you want to measure it accurately, you should make these two curves become more and more steeper, and if that is the case, you change your multiplication factor of the amplitude knobs. But keep this point in your mind: if you are going to change the multiplication factor of the input channel, at the same time you change the multiplication factor of output channel also by the same time. Say if you move from 1 to 2, here also you should move from 1 to 2. So now these curves become more and more steeper, and you can perfectly can read whether it is passing through a 0.8 or 1, something like that. So now let's measure that time period. So this is the starting point of the input, and this is the starting point of the output, and this is exactly 0.8. It is passing through 0.2, 0.4, 0.6, 0.8. So the time difference delta t is 0.8 into the multiplication factor is 0.5, right? So 0.8 into the multiplication factor 0.5, it is 0.2 by 5, it is 0.4. And to convert that into phase shift, you should multiply it by 360 into the frequency what you have set, right? That into the time period is in millisecond into 10 power minus 3. So it is 43.2. So for 45 degree, you are getting 43.2 degree, which is so closer to the value for which you have designed.